Okay, so first I'd like to thank the organizers for allowing me to present my work in this very nice workshop. I'm Marcelo Miller from the Institute of Astrophysics in La Plata, in Argentina. I'm part of two different research groups. One, which is the one where I did my PhD, which is the Stellar Evolution and Pulsation group. And another one, which is a younger group, that we started with some friends which are attending these workshops, which is the Planetary Astrophysics group. Both of them are in La Plata. So I was invited to talk about my work and given complete freedom for that. And that was at the same time a curse and a blessing, because now I was not sure what to talk about. So in the end, I decided to talk about the central stars of Planetary Nebulae, which is a topic I have been working for many years. In fact, I did my PhD on them. And that means that I'm not going to talk about several of the works have been involved in the last years also. So as this workshop is intended to foster interactions and new collaborations, I thought it would be interesting to first talk a bit about the things I'm not going to talk about, and then start doing this talk about central stars of Planetary Nebulae. So and the things, my main research topics are focused on the late evolution of low and intermediate mass stars, or stars initially below 10 solar masses, let's say, and all these late phases, let's say asymptotic giant branch, post-asymptotic giant branch, and of course central stars of Planetary Nebulae, which is the one I'm going to talk about today. Hot dwarf stars is another hot topic right nowadays, and then something I'm very interested in is the study of pulsations in hot compact stars, in particular in hot subdwarf stars and in white dwarfs, and also in the use of these pulsations to learn about the internal structure of these objects, which is what is usually known as astroseismology. And of course, I'm very interested since the very beginning of my career in several topics related with the stellar structure itself, which is like convective boundary mixing and toy models for stellar structure. And also, I've done some work in using stars as laboratories to test our knowledge of fundamental physics. Which, I mean, they are very nice laboratories for some kind of very dense materials which we cannot attain in laboratories here. And of course, in the last 5 years, 4 years, we have started this group with, in particular, with Paula Ronco and Octavio Hilera, both of them attending the workshop in the study of planets. And I mean, they know, they have been working in this for a longer time, but I just joined them and we created this group. And in particularly dealing with the formation and evolution of planetary systems, and in particular these planet interactions and star-planet interactions too. So if you want to know which kind of work we do in this group, you can see the talk by Paula Ronco and also the poster by Octavio Hilera, and you will get a very nice feeling, and they're very nice. So you should check them. Okay, so now we can start with the central stars of Planetary Nebulae, which is the main topic of this talk. I mean, the only topic, in fact. So I would like to make some brief introductions just to set the definitions and so that everybody is in the same page. Okay, so we know that low mass stars like the sun, once they finish burning helium in the core, they evolve to the red giant branch, and then at some point, once the core is massive enough and as a consequence hot enough, they will ignite helium. This will happen in a flash for stars like the sun, and they will settle on the, let's say, what is called like the red clamp or the horizontal branch, depending on the envelope in particular. And and once helium is, and during this phase, they will burn helium in the core, and at some point helium will be depleted, and they will move again, they will expand again, and they will be red giants again. I mean, this second phase is usually known as the asymptotic giant branch. The asymptotic giant branch is a phase where you have the stars have several things we will talk later, but in particular, at some point, the star will lose the envelope and it will start contracting back not back, but it will start to contract to the white dwarf phase. And during this contraction, the photosphere will heat up and it will reach very high temperatures. And this means that they will emit a lot of UV radiation, and this is what if the conditions are adequate, it will form a planetary nebulae. I mean, it's very similar evolution is for intermediate mass stars. Everything is very similar. They burn helium, hydrogen in the core during the main sequence. They move to the red giant phase. At some point, helium is ignited. The main difference is that for these stars, helium is ignited in a very smooth way, though there's no flash. And then again, I mean, once helium is depleted in the core, they move to the asymptotic giant branch, and they lose the envelope. In this case, it's a much more massive envelope. And again, they contract to the white dwarf phase. And if conditions are adequate, they can create a central star of planetary nebulae. I mean, they can create a planetary nebulae. As a consequence, the remnant is a central star of the planetary nebulae. Otherwise, you will only have the remnant, but there won't be any planetary nebulae. I mean, the interesting, of course, I mean, binaries can also play a role. We know that some central stars are binaries. So we know that binaries can create planetary nebulae. And this can happen in different ways, but in particular, if you have a binary system, at some point, one of the stars can evolve, become a red giant. If it fills the rush law, it will start to transfer mass to the companion. And under certain conditions, I mean, if the mass transfer is unstable in particular, this might lead to the formation of a common envelope. And during a common envelope, you expect one of the component to spiral in, and the angular momentum and energy is transferred to the common envelope, and at some point the envelope will be ejected, and you are left either with a merger or with a very compact binary system and a surrounding nebulae. So this is a way where you can create a binary, a central planetary nebulae with a binary core. As I said, the progenitors of central stars of planetary nebulae are mostly AGB stars. And this is interesting because AGB stars have a very particular structure, which is they are composed of a convective envelope, which is this thing around it, which is the very extended thing, and a much more compact interior where you have the hydrogen burning shell. Below that, you have this intershell region where you have a mixture of material, in particular helium, carbon, and oxygen, which is a very strange composition to have at the same time in the surface and in the region inside the star. And then you have this degenerate carbon oxygen core and a helium shell in between them, which is this thing over here. The interesting thing is that this helium burning shell, at some point at the end of the asymptotic giant branch, it becomes unstable. And this leads to many things. In particular, it leads to several convective motions that can mix and dredge material from the interior to the surface, lead to enrichment of the surface composition. This may enhance winds by carbon. I mean, if the surface becomes carbon rich, these enhance winds. But the important thing is that you have these thermal pulses, which are regular instability of the helium burning shell, and this will play a role in the formation of some peculiar objects. I mean, a minority of central stars are known to be hydrogen deficient, and these thermal pulses play a role in that particular thing. So, as I said, normal central stars of planetary nebulae, they are just, they evolve to the asymptotic giant branch. They have these thermal pulses. You can see them even here in the HR diagram, or theoretical HR diagram. And at some point, the envelope is ejected, and they evolve and they contract to the white dwarf phase, and okay, they finally form white dwarfs. So this is the normal, let's say, the canonical scenario. But if one of these thermal pulses happen when the star is contracting to the white dwarf phase, you will have this injection of energy by the thermal pulse will lead the star to expand again to the asymptotic giant branch, which is usually called a born again star, because it in a way the star is reborn to the it's brought back to life. And depending on where you have this helium flash, you can have like different flavors of this late flash scenario. But the interesting thing is that in both, these late flashes are able to form what we call like Wolf-Rayet type central stars of planetary nebulae and PG1159 like spectra of the central stars, which is very similar in terms of the composition. It's just that PG1159 stars do not show strong winds, but that's why they do not have this Wolf-Rayet spectrum. Okay, so going to the work we have been doing lately, in the last years, Okay, so one of the things I did like 5 years ago now, I mean already, is like I created this a grid of models of post-AGV, of let's say of central stars of planetary nebulae, of post-AGV stars, and also we created some grids of models for Wolf-Rayet central stars of P11 59 stars. So we computed model for different masses, and this can be used for different things. So this led me to collaborations with different people. So those are the collaborations I wanted to talk to you about, so that you can see what the kind of things that we can do with this, we have been doing and we can do. I would like to start with the collaborations that, I mean, someone from Córdoba, because I mean, this is who are organizing this workshop. So in particular by Walter Weitmann and his collaborators. Walter has been working with central stars for a long time now. In particular, he had done this beautiful catalog of central stars of planetary nebulae. So with all this information that he collected, and so we use that information together with the models in order to try to get ages and masses for these central stars by comparing, let's say, luminosities, effective temperatures, and surface gravities to those predicted by the models. And of course, as with the models, we can draw isochrones. I mean, these isochrones are just the time, the post-HEV time scale. So this is just how much time after the asymptotic giant branch the star is. So as you can see, this is only 1,000 years, 10,000 years, 30,000 years, which is like the typical lifetime of a planetary nebulae. So we derive the masses. You can derive them by comparing both in the HR diagram, which is the one on top, or comparing them, the location of those objects in the what we call the kill diagram, which is the effective temperature, effective gravity, the surface gravity location. So by comparing in both diagrams, you can get like a mass distribution for the central stars. You can get an age distribution for the central stars. Okay, so, but one of the things is for some of these stars, what you derive from one diagram and what you derive from the other diagram, they do not, they are not so consistent. So in principle, you can guess that maybe the models are not good for these stars. But what was very interesting, I mean, this work has many other things. I mean, the work that Walter did is huge, but in particular, I would like to talk what we did with the models is that now we were able to, by keeping those objects that they have consistent ages and masses, or from the comparison with the models, we were able to show that at least for 50% of this sample that has both luminosity, surface gravity, and temperature, 50% of those objects are consistent with what single stellar evolution predicts. So they are consistent in terms of where are they located in these diagrams. So the masses are also consistent because you have masses between 0.5. This is what I'm showing here is just for this subsample that is consistent between what you get from those diagrams. And as you can see, also the ages, they have this some cutoff here, which is the cutoff that you expect from the lifetime of planetary nebulae, which is 30 kilo years, 30,000 years. And so the interesting thing from this is that at least we see, I mean, this does not mean that these objects are single stars, but it means that at least what the prediction from single stellar evolution is able to explain what we see at least in 50% of these objects that we studied, which is quite interesting because, as I said, some people in the community think that 100% of the objects are binaries, and maybe this is pointing in the direction that there is an important amount of central stars that are just single stars because they are consistent with what models predict. So okay, so this is an interesting result, at least for me. So the other thing that we did with these models was this is a work that was led by Richard Henry from the US, and so what we did was derive abundances from planetary nebulae, and then from planetary nebulae that we know the central stars, so we know more or less the luminosity, the effective temperature, and by comparing the location of the luminosity and effective temperature of the models with the NDHL diagram, so this location in the HL diagram with the models, you can get an idea of, I mean, you can get an estimation of the of the mass of the object, and this also, in a way, tells you about the initial mass, also the progenitor mass of the central star of the planetary nebulae, and also of the planetary nebulae. So by deriving abundances of the planetary nebulae and deriving the initial mass of this object, you can make this kind of diagrams where you compare, let's say, abundances, helium, hydrogen, nitrogen, oxygen, with the initial mass of the star. And this is interesting because there you can compare with the models and see whether these things fit or not. And in principle, there is a large scatter, see the error bars are not small. But one interesting feature that at least caught my attention, and you will see that why also this is we will repeat later, is that you see that there is some kind of nitrogen enrichment at around 2.5 masses, which is not predicted by the models. I mean, this is just, I mean, a hint. I mean, I'm not claiming that this is a thing, but you will see that it comes again later. So from this study of central stars and planetary nebulae in the Milky Way, there was this hint that maybe there is nitrogen enrichment at lower masses that predicted by the models, and this could be hinting at that third redshift, which is this mixing during the asymptotic giant branch that I mentioned before, develops at lower masses than the models predict, or that something that is called thermohaline mixing, which or fingering convection, that might take place in the first red giant branch, before the helium flash, for example, or the helium burning, that thermohaline mixing during this phase can also lead to nitrogen enrichment, or even rotation can also lead to nitrogen enrichment. So maybe this is hinting at something that is missing in the models. And in fact, from observations, we did a very similar thing with Fang from China, and again, like deriving like mass, like the location of the central stars, and or the planetary nebulae in this case in M31, and deriving the masses of the objects from the location in the HR diagram. You can also, using some initial final mass relationship, as I mentioned before, you can get the initial mass of the star. Let's say in this case is these diagrams over here. There are many diagrams here because they are using different models. So, and in particular, as you can see, you can get the initial mass, which is this ini, which is here. And of course, then you can look at the abundances that you can measure in the planetary nebulae. And the interesting thing is, again, that of course this is helium, oxygen, hydrogen, okay, nitrogen, oxygen, and in particular, look at this. This is nitrogen again, nitrogen over oxygen, and again, as you can see, the models predict the very flat nitrogen over oxygen abundance, which is Ini over Sun here, and up to 3 solar masses. But you still see, I mean, some points here which are nitrogen rich and low masses. So again, this is what I wanted to mention is we have this, in a way, hints, because they are not very robust, any of these, but they are from very different samples, one in the Milky Way, one in M31, where you see that the model, I mean, the models and the observations do not predict the same for the nitrogen abundance. I mean, do not show the same for the nitrogen abundance. And this might be hinting, as I said, to the fact that maybe some either third redshift begins at lower masses, or maybe some thermohaline mixing is important for this, for during the first red giant branch for low mass stars. I would like to talk about the hydrogen deficient central stars, in particular these born again stars, which are like my pet objects. I mean, I like them a lot because these are stars that are evolving in a very fast pace. They evolve, I mean, the stellar evolution is happening in timescales which are comparable with human timescales, which is completely weird for a low mass star and even for a more massive star. Okay, the first example I would like to discuss is this, the central stars of the Stingray Nebulae. This comes back to a paper by Nicole Reindl in 2014. she and her supervisors, they were studying this object, which was evolving at a very fast pace. They were making like quantitative analysis, spectral analysis, in order to estimate how fast the effective temperature was changing. And as you can see here, I mean, this is, let's say, 1988, 1997, 2006. So the star was, I mean, this is heating up thousands of Kelvin in per year. So this is huge. I mean, you can see here the effective temperature evolution here in the lower panel. So you can see that in 1970, this is come from some plates. It was around 20,000 Kelvin. Then at around close to the 90s, it was already like 30 something, 35,000 Kelvin. And then it kept increasing. And in the 2000s, it reached like 60,000 Kelvin. So they were trying to analyze it and try to fit models to this. I mean, this very fast evolution is what you expect from a very massive central star. But the point is that this star was not very luminous, so it's not what you expect. I mean, if it's very massive, it should be very luminous too, and that was not the case. Also, the surface gravity was very low. So they were discussing different scenarios. Neither of these scenarios was fitting very well. So at some point we were discussing this thing, and we came to the idea that maybe this was one of these Born-Again objects that I like so much. So the idea is that, and this is interesting, is that this, as I said, these Born-Again objects, they evolve very fast, but at some point they stop increasing the temperature and they go back to the asymptotic giant branch. They stop contracting and they start to expand and become a red giant again. So one of the interesting things, and that was very specific from this scenario, was that at some point the star should stop heating up and start cooling down, which is very different from what all the other competitor scenarios predict. So we asked for time. We got the time from the HST, and with these observations, we derived the temperature in 2015. And I mean, this was done by Nicole Reindl, which is the one that knows how to do these stellar atmosphere models, which are very complicated because they are extremely non-LTE models. And she derived the effective temperature, and that was beautiful because in fact the star was cooling down. So that was, we were finding and was proving that this star was undergoing a late helium flash, which is huge because although many stars undergo late helium flashes in their evolution, this evolution is so fast that it's extremely difficult to catch one star undergoing this phase. To put it in perspective, we only know, I mean, before this, we only knew 3 objects that have been observed during these flashes. We know that at least 20% of the post-HV stars go through this phase or something like that, but only 3 objects were detected. This is like the 4th. And as you can see, I mean, the object, as you can see, the evolution of the object more or less resembles what we get from the stellar evolution models, in particular regarding the temperature, the surface temperature evolution. Of course, if you look at this other diagram with the surface gravity, you will see that there is a shift, I mean, an offset. And this is something we don't have any explanation for that. Recently, another paper by another author with models, stellar evolution models about this object came out, and the problem is still there. I mean, what you get from stellar atmospheres is much higher gravities than what you get from the models. But the important thing about here is the qualitative thing. I mean, the fact that this is the only scenario that predicts that the star will stop heating up and start cooling down. Also the speed of the evolution of the effective temperature fits very well the model. So this was a beautiful result, and I wanted to mention it because I think it's very interesting. So the last thing I wanted to talk about is something about binaries. So to close with some very interesting binary central star, which is this. This is the central star of this Henise 2428 planetary nebulae, which was in the news in 2015 because at that time they realized that the central star was a binary, a close binary, a contact binary, in fact, a very, very close binary. But the point is that when they measured the masses by radial velocities, they found out that the total mass of the system was larger than the Chandrasekhar mass. So this means that this is a very close binary. So by the emission of gravitational waves, at some point it will merge. I mean, and only in a as I said, as he said here, like in 700 million years. So this is rather short time. And this system had a mass larger than the Chandrasekhar mass, so it was a beautiful candidate for what is called the double detonation, the double degenerate scenario for the type 1a supernovae. And here you can see the radial velocity light curves. So the radial velocity curves. And so that was beautiful because, I mean, this is a scenario that has been proposed, but there are no candidates up to this point. There were no candidates observed. And so this was very, very much in the news because of that. But already in 2016, Garcia Berro, Leandro Althaus from our group, and Noam Soker from Israel, they noted that in this analysis here, there were several inconsistencies. I mean, the total luminosity of the object was too low for what you expect for a post UV star. The fact that the masses of the components was almost the same was also very, very weird, because you expect the stars in this phase to evolve very fast. So if they have the same mass, you should not expect to see them with the same effective temperature. And so it was very weird. There were several things that were suspicious. So Nicole Reindl from Potsdam and Veronika Schaffenroth, also from Potsdam, they and some other people here like Stefan Geyer and also people from Leicester, they in England, they started to look at reanalysis of the data, and by doing again the non-LTE models of the stellar atmospheres in order to fit the lines, and and also to making better models of the light curve, they rederive the values. But in particular, there was one key point that was something that Nicole Reindl realized, that was that some of the lines that are used for the radial velocity determination, and this is very interesting because it can be affecting other determinations, they were contaminated by what is called like diffuse interstellar bands. And you can see that here, this is the spectrum of the star. So these lines here in yellow are the lines that are used for the radial velocity determinations. And in particular, this one was the one that was used by this 2015 paper. And the blue ticks here is showing where these diffuse interstellar bands are located. And as you can see, with the exception of this one, these diffuse interstellar bands are contaminating all these lines. And she realized, because when before knowing this, she noted that by using different lines, she was getting different masses. So the radial velocity determination were giving her different masses. So these are the triangles here are the masses derived by this 2015 Nature paper. These are the masses that were derived by our group, I mean by her and her student, in for using different lines. And as you can see, in particular for the lower component, the values are completely different depending on which line you take. And in particular, when you take this line, you get consistent values with the 2015 paper. But here you can see how this diffuse interstellar band affect the measurements. And here, the diffuse interstellar band are these light blue things over here. And as you can see, it affects the fitting of the two lines, of the lines of the two components in particular. And this affects what you get, the radial velocity that you get, and as a consequence, it affects the masses. And when you include these diffuse interstellar bands, that they are not moving, they are just there, what you get is a consistent result for the two components. One component with 0.60 something, and one component with a lower mass with 0.40 something. In fact, it's here we have this 0.66 and 0.42, which is here. And so, but then once you get the masses of the object, the next thing is, what are they? I mean, what are they composed? I mean, are they, how were they formed? We know that if they are closed binaries, they must have been formed by a common envelope event. I mean, there are not many other ways you can end up with this kind of configuration. But by what? I mean, what was the previous evolution of these objects? So by looking at models from different kind of objects, I proper post-HV stars. They are too luminous, so you can discard them. Looking at, let's say, what is called like main sequence strip stars, or the stars that after the main sequence they are stripped of the envelope. They more or less fit one of the locations, but yeah, they are not very good in terms of, I mean, the masses are too high, in fact. But the post horizontal branch objects, they also are too, they do not fit very well the masses. One of them fits, the lower component more or less fits what is called post-red giant branch object, which are helium cores just devoided of the envelope. But the more massive component is certainly has to have a carbon oxygen core, and it does not fit any of these other things. So after some several discussions and trying to make some forensic analysis, I would say, we try to figure out how this could be created, and we came out with the thing that one way to create this thing is if you have a 1.3 solar mass object together with a 1.55, let's say two low mass objects, one more massive than the other, but slightly more massive and relatively close, like let's say 30 solar radii. When the more massive component ends burning helium in the core and evolves to the subgiant and branch, and then to the red giant branch, at some point it will fill the rush low. But given that the mass ratio is relatively low, so it's close to 1, this means that the mass transfer will be stable. So as the mass transfer is stable, this will be a system that is transferring mass to the companion in a nuclear timescale. So this is very slow, and at some point it will transfer almost all the envelope. The system will become very wide because transferring the mass to the companion, you start by conservation of the angular momentum, the system widens, and you end up with a relatively helium core, a low mass helium core, and a more massive, a very massive main sequence star, like 2.5. Of course, I mean, this will at some relatively fast will finish burning hydrogen in the core. It will evolve to the red giant. I mean, the red giant of the object is not very extended, so they will just begin burning helium in the core. And once they finish burning helium in the core, they will evolve to the asymptotic giant branch. And at that point, they will really expand to very large dimension, and they will fill their own rush lows. Even though they are relatively wide, they will fill the secondary. I mean, the one that is now the more massive object will fill the rush low. This will form a common envelope. And as a consequence of this common envelope, the system will spiral in. The envelope will be ejected. I mean, nobody knows exactly how the common envelope works, but we know that it works. I mean, we don't know how, but we see the consequences. And in this way, you are left with something which is a carbon oxygen core, because the object already finished burning helium in the core, and a helium core together in a contact binary and surrounded by a planetary nebulae. Of course, I mean, this is a toy model, but we created some toy models, and we see that at least they do fit the location of the more massive component and also of the least massive component. So it's more or less something I would say like this educated guess. So this is a very interesting system. Of course, the main result, and it's something that you should, I mean, this is what I was doing with the models and trying to explain where it came. Of course, the most important part of this work is the fact that with the new mass determinations, the system, as you can see, is 0.66 and 0.42, and even within the error bars, it excludes the system is below the Chandrasekhar mass. So this system is no longer a candidate for the for a supernovae type 1a double degenerate scenario. So again, the double degenerate scenario already has no candidates, at least for the moment. So this was the main result. I don't want to mislead you. I mean, the main result of this work is the fact that after this reanalysis was extremely careful reanalysis, and this the discovery by Nicole that there were these diffuse interstellar bands in bothering in the analysis, that nowadays we know that this system is no longer a type 1a supernovae candidate. So yeah, that was the most interesting, the most important part. So with that, I finished the presentation, and I thank you for your patience. And I hope we can discuss about these things or the other topics that I am interested in during the discussion session. So thank you very much.